topic, but
1, 2, 3.
yeah.
Yeah, yeah. I think if we kind of let it organize organically, what we could do is put a list of suggested and if we want to organize based on that, they can.
We can also organize it by small scale to larger scales, basically. I guess that's can go like.
Yeah.
I think that
Well,
would be
that's
the
how we
natural
take
small,
scales.
intermediate, large
Yeah.
scale,
Yeah.
and then people can go into the groups.
Yeah.
And we need tutors to, at least one tutor per
Yeah.
group to
Yeah.
go voluntarily, like
Yeah,
you.
I will happily do the large scale.
Great,
Yeah.
thanks.
No problem. Well, we should probably start. It's 9 o'clock now.
Give it 5 more minutes. Give it 5 more minutes.
Okay.
Yeah, just,
How you planned that session, which is coordinating 3 groups?
yes, we were just talking about that. So we said we split it into 3 groups, and we go by small scale, intermediate scale, large scale, and we need a tutor for each group. Ben will do the large scales.
I do the intermediate.
Okay,
Yes.
great. Want to do the small scales? Don't have to, okay?
Well, it's okay, but it's
Maybe
just,
go apart.
You want to do the
I'm not so small.
Yeah,
I don't know, but
I can do the small.
We can both do it, maybe. Yeah.
Okay.
Yeah.
Maybe you find some.
Yeah.
Maybe.
Mark could
Or Patrick.
in 12.
Okay. So Mark maybe. Let's Mark
Yeah.
would be good at it.
Sorry we didn't have a chance to talk more then, but it is what it is. You know what you mean.
It appears that people used yesterday free afternoon to go out in the evenings and not
Yeah.
come back. I guess many of them forgot what I told them, that we started now.
Very possible.
Maybe we can wait 5 minutes.
Yeah.
For
Yeah,
the
wait
astronomers.
5 after.
Yeah. Should go out to the front door and lock the door at 9:05. Sorry, you didn't get here at 9 o'clock. You should have listened.
I mean,
You don't get your
there's always a
certificate.
temptation
Ha, ha,
to
ha, ha.
online as well, so we have always the online option. Today is a bit different, so we have to keep on track now. We then split up into smaller groups for the side discussions later. Well, discussions basically to like identify maybe a few questions that we have then in the final discussion or summary. The idea is that on the last day we have the questions that you will can work on in the next few years to make yourself famous.
And reach.
And rich.
And Rich, yeah.
I don't think you're getting rich. What the question is, can I find a job outside of STARFORM?
Yeah. Wait, there's Mark. I didn't see you, Mark.
Or claim you found an extraterrestrial object falling into the ocean or something like that.
Oh, yeah, exactly. Were you reading that Guardian article about Abbey Lowe yesterday?
No, I didn't read it yesterday. I read the paper in archive last week. I was like, bah. It was guide to refereeing Lowe's paper.
Actually, intermediate scale mass for star formation. So the seminar talk is at 12:30. If you want to attend, it's just a general colloquium. Okay, we start in 2 minutes.
Sounds good. Do you want me to give you like 10-minute, 5-minute warning for timing? Or
Well, I have the clock, but
I guess
yeah.
it's easy here.
Yeah.
Right there, yeah.
Well,
I think
yeah,
we should
choose
have-
then.
I brought some down here. I don't know if I'm ready with Mark to throw them, but. Okay, all right. The challenge is on, so everyone in the middle, cover your head.
We will, by the way, just to mention it, I'll send it that around by Slack. So in principle, we are, as you have seen, that the tutors are posting their talks on the Slack channel, in case you haven't seen it. We will also gather all the material, including the videos, and it will be online for later reference. I can do a little dance for you.
Does anyone know how to juggle?
Oh yeah, it's chocolates.
Yeah, exactly.
Chocolates and a stick.
Chocolate and stick.
Yeah.
How we
I guess I'm the chair, so I could get up and warm the audience up, tell some jokes.
Get the
Yeah.
microphone.
Yeah, do the dancing, yeah.
How's everyone doing today? Just flew into Grenada last night. Boy, are my arms tired.
Okay.
Yeah, exactly. We don't have to laugh. Just your supervisor.
You know that. You do have to laugh.
Okay.
One more coming. This is like rain in Granada. You get a drop from time to time, but not really a stream. So one more person coming. So we escape.
No, Mills. Okay.
Let's just start.
All right. Okay, hopefully everyone is alive after their free afternoon yesterday and an early start. Getting us started today is Ignacio, who's going to get weird with it. Today's session's on extreme environments of star formation, and we're going to hear about some of the nearby ones. So take it away, Ignacio.
Okay, good morning, everyone. As Maya said, we are now at this stage where we are moving from small scale to larger scales, and Angela gave us an introduction of what we find in the local group. But I'm going to sort of cover the region between Nuria and Angela now, and concentrating a bit on the heavyweights of the mass distribution among clusters. This is important because most of what we know about star formation is based on a few star-forming regions, which are mostly low mass. The Taurus star-forming region, the Perseus star-forming region. There are low mass places where you form small clumps of low mass stars. And of course, this doesn't connect directly with the sort of clusters that Angela was showing yesterday. But the galaxy is big, and there are many other things. So let's have a look. So we're looking at open clusters as useful laboratories for astrophysics in general and to understand star formation. And the solar neighborhood, there are many clusters, and typically they have masses between 100 and 1,000 solar masses. This is the lower limit is probably what you call a cluster. Maybe Nuria doesn't, but you need at least 100 solar masses to be gravitationally bound. The upper limit was found many years ago. Let's see, for example, this paper in which they analyzed 100 clusters up to 2 kiloparsecs found typical mass is about 500 solar masses. This is probably no longer valid. I was actually looking at these at some overheads I had from about 10 years ago, and I thought many of these things are not valid anymore. But I'm going to keep them and show you, because there are many interesting things in this literature that you need to look at, and it's probably better if I just signal what's changed. And when people were doing this, we had a very little understanding of the low part of the IMF, so they were probably underestimating masses. So this is probably outdated now. Then there was the famous Lada and Lada paper, which claimed that the number of embedded clusters suggests that 90% of the stars are formed in protoclusters, meaning what someone said the other day is star formation is clustered. Doesn't mean that they form in real clusters, but most of them disperse before becoming optically visible. And they found the IMF was pretty universal with a broad maximum around 0.6 solar masses. This is not believed anymore. The Herschel data showed that this wasn't quite the case. Now we have better observing techniques, and the maximum you saw this discussed yesterday is probably around 0.3 instead of 0.6. The kinematic analysis that Nuria showed us based on nearby associations, Gaia data, are not really compatible with this idea that most things are clustered. Most things just form loose groups, at least in the solar neighborhood. So Related to this is this question. There appears to be a very good correlation between the mass of a cluster and the mass of the most massive star that you find in the cluster. And this, of course, can be interpreted in many different ways. This is a correlation by the group of Pavel Krupa that you see here. Some people don't believe that this correlation even exists, but they are very keen on saying that this is the case. But even if it exists, there's a big argument about whether this means anything. Because, of course, if you have an IMF that says that a very massive star is very unlikely to form, say 1 in 1,000 is a very massive star, and you have 200 stars, then it's unlikely you will find a very massive star. If you have 20,000 stars, then it's much more likely you will have a very massive star. So it may be simply a consequence of the statistical nature of the IMF that you sample stochastically and you get this sort of correlation. Again, there are people, including Pavel Krupa and many others, that think that no, this has to do with how massive stars are formed. You require clusters to form massive stars. You require very big clusters to form very massive stars. And there's a lot of argument about this. And personally, I'm not completely convinced by any of the two sides. So, but some people, like Mark, I think are completely convinced by his side. Okay. But in general, what you see is that to form some massive stars, you need about 1,000 solar masses. And you want to get 1,000 solar masses, that you need to go to a Orion Nebula cluster that we said is at 400 parsecs, and is our example of a real cluster. So the total mass of the molecular cloud, as was mentioned, is about 100,000 solar masses. You have a few small clusters and now a 1,000 solar mass cluster. So this means that only a small fraction of the gas is being turned into stars. And there were a lot of arguments yesterday about the efficiency of the star formation and where it may come from. On the other hand, people also talked yesterday about this, is positive feedback. You have massive stars that are perhaps destroying the clouds around them, but they're also causing some other effects that may induce a star formation. And the idea is this: you have a very big cloud, you form a small cluster on one edge or in the center, then the energy that the stars will inject into the cloud will produce new shocks, new regions of high density where you can have other clusters forming, other stars forming. And this is the idea of triggered star formation. It was proposed many years ago. There's a lot of observational evidence that seems to favor triggered star formation. A lot of the old theoreticians believed in triggered star formation. Most of the people who do theory nowadays don't believe in star formation, in triggered star formation, because they say it doesn't appear in the models. But most observers believe in star formation, because in triggered star formation, because they see things that can be very easily explained with triggered star formation, like here where you have the big stars up here and they're illuminating this, and you can very clearly see how this is photodissociating, and here you have the dense clumps where new stars are being formed. So is this because it's being induced by the massive stars, or is it simply that it's being formed and the massive stars are cleaning away the areas where there are no stars? This is the argument. But if you have something like that, what you have is that over the scale of a very big cloud, which are typically 10 to the 5 to 10 to the 6 solar masses, you're going to have successive generations of clusters propagating star formation from one side to the other. This is an easy way to explain low efficiency in gas-to-star transformation, leads to the dissolution of low-mass clusters, can explain cluster formation as a local process, but at the same time can give you associations that happen on the typical size of a molecular cloud, giant molecular cloud, which is perhaps 80, 100 parsecs, as you see in external galaxies. And you see, for example, here the work by Nuria, in which the distribution of things in the Scorpius-Centaurus complex can be explained by something like that. In fact, the idea that the Scorpius-Centaurus complex is telling us a story of sequential, at least sequential, perhaps not triggered, but at least sequential star formation has been mentioned at least 30 years ago. Okay, but of course, as Angela showed us yesterday, there are other environments in which you have very different things. You have huge clusters. And this is generally connected to the starburst phenomena that happen mostly in places where there's interaction between galaxies. And this means there's a lot of things going on. There's a lot of turbulence. There are lots of shocks. There are clouds falling onto clouds. And there you see things like this, which is a irregular galaxy in a starburst. You see here a spiral starburst, and you can see here this is the blue is the massive stars, the red is the H-alpha, and you can see well, there's a lot going on in that galaxy. And in these sort of places, you form lots of very big clusters. And you see places where people look for these sort of very big clusters, like the antennae galaxies, which are obviously interacting, like the Stevens Quintet, where the galaxies are interacting. You find very massive clusters in these environments. Since the development of infrared instrumentation, people were able to find what they call ultra-dense giant H2 regions, which were extremely compact and had inferred masses of a few million solar masses, and are supposed to be the progenitors of these huge clusters that you see in those environments. And what you see, I mean, Angela showed this for the local galaxies where you don't go up to such high masses, but there's a continuum of masses from our typical galactic cluster to the most massive superclusters. So what changes in their conditions? I mean, what's different? We don't really know. And there's another question which is pertinent, and I guess will be addressed tomorrow, is we have the globular clusters. They are huge clusters, formed at some point. Are they the top of this continuum, or they were formed under different conditions than current day clusters? It's an important question to understand how the stars in the galaxies were formed, because our understanding is that you had a lot of star formation in the past when these things happened, and it had been decreasing steadily since then. So the star formation that we see there now is forming a few stars, but most of the population in the galaxy were formed many billion years ago, and were formed under different conditions from the Taurus cloud that we see now. So we need to try to understand what goes on when things are messier and denser. So places to look, for example, this is what people used to call a young globular cluster in the Large Magellanic Cloud. It looks like a globular cluster. It's young, so let's call it a young globular. This is NGC 1755, which is about 60 million years old. It's very well studied. These things are red supergiants, and the rest of the things are B-type stars. It looks like a globular. It's certainly not a globular. This is a quote from Larsen and Richler, 1999. These LMC clusters are not quite as spectacular as those found in the starburst. They are still more massive than any of the open clusters in the Milky Way today. But this is not true. And this is not true in two accounts. It's not true because we have massive clusters in the Milky Way, only we hadn't realized 20 years ago. And it's not true because these things are not as massive as they thought. I don't know why. They were overestimating their masses by a serious amount. That young globular has a mass of, probably looking at its population, of perhaps 30,000 solar masses. So it's extremely short of a globular cluster. The only two clusters in the LMC that come somewhere close to the mass of a globular, but of course are much younger, are NGC 1850 that may be around 100,000 solar masses, and it's about 100 million years old, and 32, of which more later. Okay. So, in the galaxy, we are more modest, and it was decided 10 years ago that we're going to call a massive cluster something that was more than 10,000 solar masses, which is big. It's 10 times Orion, and for the local environment, looks okay. It's not your usual thing. It's an order of magnitude more. And there are quite a few of these, in fact. But simply we weren't doing things right. This is, for example, a cluster in the Perseus arm, NGC 663. It's nothing spectacular, not very well studied. Estimates from the 80s, 800 solar masses. But with Gaia, I can tell you that there are more than 400 B-type stars in this image. And I have a spectra for about 1/3 of them, so I'm sure they are B-type stars. And that means you have about 2,000 stars, 2,000 solar masses simply in B-type stars. So that means it's a much more massive cluster, and it's Perseus arm, nothing spectacular. And what's even more interesting is that this cluster is part of an association which is known as CARS-OB8. These are Gaia data. These two other clusters have essentially the same proper motions and distances. And when you look at a whole, there may be perhaps 800 P-type stars here, so 20,000 solar masses probably. And of course, it's a bit distributed. You look at the size here, these are almost 2 degrees, so maybe 30, 40 parsecs scale of a giant molecular cloud. So we have big things in the solar neighborhood, only they were a bit hidden. Just to give you an example, this is a very distant and obscured, yeah?
Can I interrupt you?
Yeah, of course, anyone can interrupt me.
This is driven very much by personal interest of our own research, because we are looking for massive clusters in the center of the Milky Way. Of course, you cannot see them, but we think we find some of them with proper motions, but they are associated maybe only with 1 or 2 very massive post-main sequence stars. So I wonder, why have these things been hidden? I mean, they obviously do not contain many O stars. I mean, if we have B stars, we can easily hide that stuff in the galactic center. So is that, why were they so hidden? Have all the O stars disappeared, or do they not sample the IMF up to very high masses?
In these cases,
there's no red supergiants, yes?
No, these are older. These are about 20 million years old.
Okay, interesting. Thanks.
Yeah, that's why you haven't got any O-type stars, and probably they have started expanding, so they are not so concentrated. So you take these 2.6 kiloparsecs behind a lot of extinction, you probably don't see it at all. I'll come back to this in a moment. These are, a few years ago, there was a lot of interest in this region because it was supposed to be the most massive star-forming region in the Milky Way, but I haven't heard much about it. It's very far away, it's very extinguished, you can only see it in infrared. There was this claim, there was a lot of clusters being formed, and at least one of them had more than 100 type stars. Since then, there's only seen this paper by Roberto, who is sitting there, and these are the paper with sun spectroscopy. It's probably not quite as big as they were saying, but it's a big area, and this is probably the sort of thing that produces an association like the one I showed you, but this is about 8 kiloparsecs away and extremely obscured, so it hasn't been well studied.
Can I add something?
Yeah, of course.
We are observing it a lot with the VLA and ARMA. We are also detecting embedded O-stars, but seen in the radio continuum. So it has a lot of stuff.
It has a lot of stuff. It's the younger version of what we just seen. This is another very big star formation that they call the dragonfish. I don't know if anyone sees a dragonfish there. I'm not even sure what a dragonfish is, but if anyone sees a dragonfish there. It was proposed a few years ago as the most massive of the association in the Milky Way as well. It's also extremely distant. You can only see it in the infrared. But then, these people were radio astronomers. So they conceived, okay, you see a cavity here, so there must be a cluster here. So they went and took a spectra of things there, and they published this paper saying, I've seen all these O-type supergiants in the middle of the cavity, when they were clearly showing the spectra of red clamp giants in the foreground. Yeah, that happens when you go into an area that you don't really know. In fact, there was this paper by people from Madrid afterwards where what they found is that there are a lot of clusters, some of them pretty massive, formed around this ridge, and this is what is producing the luminosity, and you don't need anything in the middle to create the bubble. And it's a big star-forming region, also embedded. There are quite a few of those, but this one is they claim at 12 kiloparsecs, which is very far away. W43 is a bit closer. It's a big complex which is forming probably more than 100,000 solar masses, and it has a very compact cluster which is called W43 main, which has some extremely massive stars. It's like a blob. They are all concentrated. It's extremely young. You cannot separate them, the very massive stars there. And it's an interesting place to look, but again, only infrared. There was also this claim about Cygnus OB2. Cygnus OB2 is a nearby association. This is this paper from 2000, young globular cluster in the Milky Way. Jürgen Knödel-Seder is a gamma ray astronomer. So he found a lot of gamma rays coming from this region. Rays can come from the winds of O-type stars. So he thought, okay, there are lots of O-type stars. It's a young globular cluster. In fact, it's not. It's another association. It's a big one. This is a recent paper. You can see the distribution. There are lots of them, but of course, these are 2 degrees at 1.7 kiloparsecs. This is not a globular cluster information I can promise you. In fact, work by Nick Wright and collaborators indicates that this region formed exactly like this. This is not expanding. It's just that you form a small clump of stars with a few O-type stars here and here and here and here, and they are close by, but not related, not gravitationally bound at all. So you can have very big associations that are formed without having an obvious concentration. But we have proved that these much more massive things form in the Milky Way. This is Messier 11. From the name, you can guess it's been known for some time. People call it the wild duck cluster. Again, if anyone sees the wild duck there, just tell me. And already in the 70s, star counts, direct star counts, because this is a nearby cluster, very bright, known by Messier, were giving 3,000 solar masses. And nowadays, we have much better data. We know the age, which is about 250 million years. Present-day mass is about 10,000 solar masses. Anyone can make a guess of how massive a thing like that could be when it was young? No. Students. Yes. Chocolate.
Yeah, I have a lot of chocolate.
One mechanism would be evaporation, so stars leaving the cluster.
Yeah, that's one mechanism. That has to do with what we were mentioning yesterday, the typical velocity dispersion. So gravity holds them, but some of them go. More mechanisms to get rid of mass. There. Yeah, very obvious. Feedback? Which sort of feedback? And how do you get rid of stars with supernovae? They explode. Yeah. So the more massive stars explode. It's not exactly feedback, it's probably death in this case.
I guess it depends on whose perspective.
Yeah, exactly. What is death for someone is food for...
One cloud of gas's feedback is a star's death.
Yeah. Even B-type stars will end up their lives, produce white dwarfs, and just lose the rest. And all these mechanisms is difficult to estimate. Death of the massive stars probably takes away about 1/3 of the mass. The dispersion mechanism depends on where in the galaxy the cluster is. If it is towards the center and is on the plane, it's probably going to be a lot going on, and lots of stars are going to be lost. If it is far away from the center, then it's probably going to be more stable. But if it has 10,000 at 250, you can be pretty sure it had 20,000 at least when it started. And as you see, this is just a nearby cluster. There are quite a few more. This is Messier 37, also a well-known cluster. Star counts tell you this is about 5,000 solar masses now. It's about 350, 400 million years old. It's in the outer galaxy, so it's probably lost less mass, but probably was a 10,000 solar mass cluster when it was born. So there are many of these, and even bigger ones if you know where to look. In fact, this is you remember Nuria talked about these Bayesian algorithms that go around Gaia data to find clusters. This is the distribution of young clusters in the catalog of catalogs of Hunt and Redford. Here, center of the Milky Way is here. Sun is here, where this blob is. The blob is obviously artificial. It's due to the fact that close to the sun, we see a lot of low density, small groups that the algorithm and Nuria call clusters. But if you go a bit further away, you are not going to see them. So that's why we have the blob here where the sun is. You have the galactic center here. So if you go in this direction, you are coming out of the galaxy, and you see how the density is going down. These are young clusters. I picked 80 million years because their error bars on ages are generally huge. You see that density of clusters is going down. There are two reasons for this. The main one is, as we saw yesterday, the surface density of gas is going down, so star formation is really going down. The other is that they are far away, and so when you come here, I don't know, 8 kiloparsecs from the sun, you combine that with sun extinction, and typical solar-type stars is magnitude 23. Gaia doesn't see it. An A-type star is close to the limit of Gaia. You don't get good proper motions, so you don't see that there's a group there. But it's true that this is really going down as you move out. As you move in, you find this. This is extinction. This is, in fact, this is this. This is the map of molecular clouds, and it's turned around 90 degrees. This is that. This is the wall that we call the Scutum-Crux arm, and happy to put a wager that a significant fraction of the star formation in the galaxy is happening there. It's just that we don't see it. It's just cloud after cloud. It's very, very dark. So with that knowledge, I'm going to show you the young, massive open clusters in the Milky Way that we know about. Again, this is all the way around. This is 180 degrees turned. Sun is here, galactic center is here. I've marked here the Perseus clusters, which are big, but not quite massive, but they have big associations around them. And here we have little contamination. We can see easily those associations. This is Cygnus OB2, also an association. And then we have this line of sight that goes this way, what we call the Carina region, where we have the Carina Nebula, which is a huge association that contains two very big clusters. And following it, we have Vestalon 2, which was shown yesterday several times because it's very beautiful, the star-forming cluster, and NGC 3603, which is far away and is nice as well. Everything else is behind the wall, and so we know little about them. So the most obvious feature here is this, which is what I call the Scutum complex, because it's in the Scutum constellation. It's a collection of red supergiants, an enormous collection of red supergiants. There are at least 4 big clusters, some of which, as you can guess, we discovered, that contain lots of red supergiants. But the extinction is so high that you only see the red supergiants. You see them in the infrared because they are extremely bright. These things are like absolute magnitudes of -10, -11 in the K-band. So yeah, it's like, you see them. But we don't see the main sequences of these objects, so we have no Gaia data. So we are just guessing about this masses. It's because they have lots of red supergiants, they have to be very massive. We cannot learn about star formation much, but that's a pity because, of course, you wonder why you have this concentration here. And if you look at a map, it seems to be the place where the bar ends and the arm starts. So you can make a guess about why this is happening, but we haven't got the tools to understand what's going on. In fact, W43, which I just showed you, is here, the big star-forming region. But interestingly, there are 2 more clusters like those here with lots of red supergiants, and these ones are in the middle of nowhere. And the view to these ones is a bit better. You can see the main sequences. Gaia is almost there. And what's surprising to me is that Gaia claims that these 2 things are not together. One is about 800 parsecs in front of the other, which may be that there are some residual issues with Gaia data that we don't understand yet. Maybe. I'll wait for DR4. But it also may mean that basically you have a corridor in extinction here, and what you are seeing is telling you that these 10,000 solar mass clusters are pretty common in the inner galaxy. It could be. It's just this extinction wall that doesn't let us see anything. And then you have these Mercer clusters that come from the Mercer catalog, which were found with Spitzer. That means that these things are only obvious in the mid-infrared. So put them there, but really we have absolutely no idea of where they are and how massive they are. It's just people who found them claim they were very massive, so I put them. And then there's this other concentration here, which is just in the middle. Conditions there are a bit different from the Taurus molecular cloud, but John is going to give us a sensational lecture about this in a few minutes, so I'm not going to go into that. Just to show you how these things look, this is NGC 3603. It's very far away, which is a pity. Lots of very bright stars. Then, in fact, as we study the cluster, the number of L-type stars has been increasing. It's extremely young. It's less than 2 million years old. It contains this object. Well, this is a bit of the spectrum of the object, which is an SB2, what's B2-ish system that has been solved spectroscopically and contains the more massive star for which we have a measurement. This thing here that you see is an emission line in the infrared. In the 90s, people found varieties, the true Wolf-Rayet stars that were just exposed cores of stars that have lost their envelopes for some reason. And then the hydrogen-rich Wolf-Rayet stars were a different breed. These are extremely massive stars that happen to have winds that are so thick that you don't see their atmospheres anymore. And the most massive stars, at least in our environment, show this morphology. So they're extremely difficult to study. But you can see here that the emission lines have like 2 peaks that they interpret as the 2 stars. Problem is that, of course, the
error bars are huge. We have now a few objects that can close to the lower limit of the error bars, but nothing that has been solved, really solved, that is bigger than this. Of course, these things have huge winds, and then you have to go to your favorite stellar model and say, well, if it has 120 solar masses now, how much did it have when it formed? Then your favorite model may say something, but it's probably 50% more, 160, something like that. Distance has been guessed correctly. It's at the limit of Gaia, but it's somewhere around there. It's just 7 kiloparsecs. Mass is probably 15,000 solar masses. Big cluster. In the middle of the galaxy is the Arches cluster. The Arches cluster is 100 parsecs away from the center of the Milky Way, and that means it's almost impossible to observe, as Rainer knows very well. There are all sort of issues with these things which are behind 30 magnitudes of extinction, which means that even in the infrared, you have all sorts of problems. And in fact, this is the history of the Arches. It was discovered in the late 90s. Don Feiger found that there were many massive stars and with more than 100 solar masses. Then the people from Heidelberg found that it was top-heavy IMF. They said, okay, it's close to the galactic center, conditions are weird, so it's top-heavy. But then it's top-heavy. This means severe depletion of intermediate and low-mass stars. So maybe it has a lot of massive stars, but it's not so massive. You cannot use the same sort of relations that we are using in the rest of the galaxy. But then people were saying, okay, but you are not doing your photometric transformation right. And we have to reshuffle everything, and we are not detecting the low mass stars because they are too faint. Now it's really 20,000 solar masses. Oh no, the extinction law is not what you were using. It's again 20,000 solar masses. There's this dynamical estimate, 15,000. And then there's a paper this year, by Simon Clark. Almost all very massive stars in the Arches are at least binary, which means that all the masses are wrong, basically. He confirms spectroscopically at least 120 O-type stars. There was this paper by Don Feiger in 2005, which was very famous. Essentially, he said that with the data they had, this is Salpeter's law going up, and these are the data. And he said, okay, there's a truncation here. You're not going to find, nature is forbidding you from producing stars more massive than 150. Of course, if you change the extinction law and everything, you can say 100, you can say 200 is tough. These are data from the Clark paper. This is the upper Hertzsprung-Russell diagram. They solved this binary, which you can see how they look, these sort of objects. These are infrared spectra. It's all emission lines. It's really tough to get accurate masses with this. They found this thing, which is an 82 plus 60, is this thing on the top. So mass is right. Luminosity is different. Yeah, again, this is about 2 million years old. You have to interpret what 82 now means when it's formed. But between 100 and 150, probably. That's what you get at solar metallicity. And finally, Vestolum 1. I already mentioned this the other day. This is the big guy in the neighborhood. Problem is, it is behind the wall. So how do we see it? Well, we see it because everything here is humongous, basically. It's 4.2 kiloparsecs. It has about 12, well, it's very variable between 10 and 16 magnitudes of extinction, depending on which part of the cluster you look at. That's why everything looks red in the image, which is optical. When we found this guy, we counted at least 150 volt massive stars. If you assume that there are more than 30 solar masses, for a standard IMF, that gives you 100,000 solar masses. You can argue that maybe it's 25, it's a bit less. And stack counts in the infrared imply
a minimum of 50,000 solar masses. So it's a really big cluster. It's a really big cluster. This is from the Gaia data paper I published last year. You have all the population here, red supergiants, yellow hypergiants, blue hypergiants, blue supergiants, all sort of massive stars doing weird things. It's about 5 million years old, which is when you have all sort of things happening, binaries interacting, stars turning into Wolf-Rayets. It's very complex. And the main sequence, the top of the main sequence is about down here. These are the late O stars. So you see magnitude of around 19. So it's tough to look at it, but it's nearby, and it's the only one of these clusters where you can really have a look at what is around it. So there's this big collaboration that for some reason ended up being called EWOX, which is led by Mario Guarcello from Palermo. It's trying to understand what's going on in this cluster, looking at the low mass population. This is really interesting because it's looking for the low mass population in a starburst cluster. And this is using basically Chandra X-rays. It has a 1 megasecond observation with Chandra and a lot of observing time with JWST to look for the low mass population of this cluster. And this is a very big collaboration. If anyone thinks that they can contribute in any form, be it data-led or theory-led, Mario is more than happy to add people to the collaboration. So contact him. And last but not least, the Tarantula, the largest starburst in the local group. This is outside the galaxy. This means it's much further away. This implies two things. First, distance modulus is 18.5. So your solar type star there with a little bit of extinction is a magnitude 23, 24, a bit difficult to look at in the optical. But the main problem is confusion. I mean, Westerlund is 4 kiloparsecs away. This is 50, so it's a factor of 10. Everything is bumped by a factor of 10. That's a lot. This is the LMC, and this is the starburst, and you can see it's big. It's a substantial fraction of the galaxy. Nowadays, most people are convinced that the LMC is a small spiral that has been disturbed by tidal interaction, probably with the SMC, and this has led to a burst of star formation, most of which happened about 30 or 40 million years ago, which is why you have these young globular clusters, but still going in this particular region, which is where we find the tarantula. Well, nice image, the tarantula. You see huge amounts of ionized gas. This bright gas is ionized hydrogen. Lots of clusters. There's a cluster here, for example. But of course, at 50 kiloparsecs, you cannot resolve distances. So maybe this cluster is 2 kiloparsecs in front of the tarantula. We don't know, really. You cannot infer distances with that accuracy. But the action is probably in these bubbles, and the main action is here where you have lots and lots of stars. So basically, this is the central region of the tarantula. This is NGC 2070, this area, and this is R136, seen by Hubble. R136 comes from this paper, 1960. Simbad doesn't like R136. It's too short for Simbad. It's RMC 136. You will not find it if you just key R136. The brightest stars in the Magellanic Clouds. It was taken from South Africa with the Radcliffe telescope. So it's the Radcliffe star 136. And the fact that it is in the Radcliffe catalog of bright stars means that with a 2-meter telescope from the ground, you think it is one star. And there were, in the early 70s, there was a lot of discussion about this, whether this was a 1,000 solar mass star. But of course, if you then have Hubble, you look at the star, and it doesn't look like a star anymore. It looks like a lot of stars. So, the whole region is about 1 kiloparsec across, which is very big. And the 30-door cluster, NGC 2070, spans about 40 parsecs, which again is too big for a cluster. It's a typical association. And R136 is 2.7 parsecs in radius. And you remember Angela's talk yesterday. All clusters have these radius for some reason or other. And contains, from paper in the 90s, in the 90s, first HST observations, about 4,000 stars more massive than an A-type star, which is quite a lot, indicating masses of about 40,000 in stars more massive than the Sun, close to 100,000 in total in this one star. Of course, this is a very interesting environment to look at, and people have been doing this over the years, dedicating a lot of effort and observing time. This is the VLT Flames Tarantula survey that was led by Chris Evans and has been running for the past 10 years. Well, the observations finished in 2 years, but they have been publishing papers for the past 10 years. This is the first paper. They collected spectra for more than 800 OB stars with flames. Flames has a field of about 20 minutes, so they collected from the whole area, not just from the central cluster. And this is an interesting figure for the first paper. This is a list of objects that were marked as photometric candidates to young stellar objects. And you can see here an early O-type star, an O supergiant, another O supergiant. These are not young stellar objects. So when you go to SIMBAT and you see young stellar object marked, don't believe it. It's probably any other thing. These are just photometric catalogs, which are a bit dodgy. You see these strong emission lines in every single star. These come from the nebula. They're not part of the star. It's just that everything is so compact there that you cannot remove the sky correctly. So you get these lines from the nebula. And as you can see, the nebula is very highly ionized. You have emission lines of everything here. So all the Balmer lines have things in the middle. Some of the helium lines are also in emission. There are oxygen lines. A lot of things coming from the nebula. So it's a bit difficult to work with this. You need high resolution to make sure that you're really getting the star. People have continued, especially groups in Amsterdam and Leuven. They're creating more and more campaigns, using more and more VLT time, looking for massive binaries, B-type binaries, everything. They're producing more and more catalogs. Okay. Just to give you a flavor of what they find, this is paper 11 from 2013. Basically, they take all the stars that they have observed spectroscopically, put them in an HR diagram. These are real Wolf-Rayet stars, which are to this side of the main sequence. These here are the hydrogen Wolf-Rayet stars, which are the most massive stars. This is for the whole region. This is for the central area around R136 only. And you can see here, this is the ionizing luminosity that you get just from the stars you have here. This scale is in 1 to the 52 number of photons, ionizing photons being produced. by the whole region. This is for the central cluster. Here is just 8 times to the 51, so it's a bit less. Because the most massive stars produce most of the ionizing photons. And here, what you have is what they call the wind luminosity, which is a measure of the amount of energy and angular and momentum you are getting into the medium, and it's measured in x per second. Yeah, and as you can see, it's 10 to the 39 in both. So it's an enormous amount of energy you are putting into the medium. So it's certainly giving some feedback. And here we can measure it. Just each star is contributing so much. This is the paper 29, where they do is. This is a bit dodgy, but it probably works. From the spectroscopic properties, they place stars in the H diagram and assign an age. Then they don't do it directly, but they use a Bayesian algorithm to say what is the statistical age of this star. And now they plot them. Here you have the ages. White is 0. Dark blue is 8. So they plot the distribution of stars. Well, it's a mess, basically. It's a mess. So they conclude that there's no large spatial structure here, and that there's been star formation going on in the whole region for the past 8 million years. It started slowly, just a few stars being formed about 8 million years ago. Then you had a burst that produced this smaller cluster, 2060. About 3 million years ago, you had things accelerating in this region, producing lots and lots of massive stars, and culminating with the creation of the central cluster about 2 million years ago. That's the picture you get from this. The cluster formed monolithically about 2 million years ago. As I said, take it with a pinch of salt, but there's some truth to this. Then the biggest star in the middle is very big, and in 2010, Paul Crowther published a paper claiming that it had a current mass of about 250 solar masses, implying more than 300 originally. How did he calculate it? Well, basically, he used these systems in which you have a spectroscopic mass and sort of extrapolated the luminosity to the luminosity of this thing. This is very controversial. It's not clear why in the galaxy it's just 150 and up there is more than 300. It depends a lot on the extinction law and how you treat your photometry and everything. But I think most people nowadays are happy to believe that this was somewhere between 200 and 250 initially. But of course, the problem you have is that the spatial resolution is so bad that you're never sure if this is a single star. Because you've seen O-type stars generally are all multiples. So people are still working on this. This is a paper from this year by Chenard. They've taken HST images of the star. This is the brightest one, and second one, third one, and analyzing how the PSF looks around the slit to see if there's something hidden there or not. They are doing the same with the radial velocities to be sure that there are no binaries, close binaries that you cannot see. People have still not found binarity for this star. No, maybe a bit surprising. Well, massive stars have companions. The most massive star hasn't got any, maybe, but I mean, people are really working hard to try to understand whether you can have a 250 solar mass star or not, but it's not settled. This is, for example, something they're doing with the Hubble. They just put in a slit, and they're observing all these stars. You have there an estimate of the mass of the stars you're getting, and you see it goes from 20 to 100, so they are all pretty hefty stars, and they take a spectra of all of them and try to understand how things are going. This is another recent paper from the same group last year. They look at the 51 single line type binaries and determined the masses of the companions. And as you can see, except at very low mass ratios, where you have obviously a lot of problem detecting the low mass star. This is, they claim, sort of compatible with completely flat distribution of secondaries in binaries, which is a bit surprising because you tend to see stars in which the two components look the same, but they say if you really do it well, you see a flat distribution. Whoop, killed it. There's not much left. Just to finish, the JWST view, you can see it's spectacular. Well, the advantage is, you are very far away, but you have a very big telescope. You're looking in the infrared, so you can see low mass stars. They may be very close together, but of course this has a very, very high spatial resolution. So it's just another place where maybe you can look at the low mass population of a starburst cluster. So this is a paper that came out 2 weeks ago in the archive. This is CMG for a central field with in the mid-infrared. You can see you're getting down to magnitude 25, which is, well, okay, but I'm not very sure what it means in the mid-infrared. But certainly, well, these are all low mass stars. And you can see there are a few. They plot this distribution. This is basically measuring the distribution of gas. These are the ALMA contours, which are, the dust. This is the ALMA contours, which are probably giving you the gas. And this is the distribution of different kind of stars in the area. And here, unlike the previous paper, they claim that it's clear that star formation is coming this way towards the big cluster here. Not very sure whether they see this with these images, but this is the conclusion they reach in the paper based on their analysis that there's a star formation coming from a... Yeah, they basically divide these into age ranges, and they claim that it started about 6 million years ago here, and it's moving in this direction, and then you have most of the action going on here in the last 2 million years. That's what they claim in this paper, and that's what we are. So this is what I wanted to show you. Just to finish, I want to propose an exercise for you to think. You don't need to solve it now, but just think about it. If I tell you that a cluster has a normal IMF, and I take a few spectra, and I can tell you that there are 20 stars between 5 and 10 solar masses, how would you calculate the total mass of the cluster? It's an interesting thing to think about, because normally we have that sort of information. As you have seen, we have the top of the main sequence. So I have 20 stars between 5 and 10 solar masses. How would you calculate the mass of the cluster, assuming that statistics work? If you have any questions, please shoot. Overwhelmed.
I'll just comment. I don't think that Krupp is necessarily wrong about the IMF depending on the cluster mass. I just don't think that the evidence that has been presented is anywhere near sufficient to establish the claim. I just want to clarify. He could be right. He just insists he's right when the evidence doesn't show it.
Yeah, lately he's been using beauty arguments, which seem a bit off. Yeah. But essentially, what he's claiming is that the star that is forming has a way of knowing where it is. Basically, that's from the physical point of view. That's the difference between the two sides, or the two ways of looking at it. Two stars, as they form, sense the difference between being in a dense cluster and being in a low mass environment or not. And this is where all these models that was shown the other day, like the competitive accretion and so on, come in.
We've got time maybe for one more question, if there is one. Yep.
For the extremely massive star, when you mentioned they've not found a binary companion, even though it's expected that all O-type stars do have companions, have they ruled out the possibility of a companion, or have they ruled out any specific parameter spaces that this companion could exist in through the observations? Or have they just not happened to find anything?
Well, there are spatial scales you can sample with the observations you have. And that's what you can rule out. I mean, that paper I showed you, they can rule out that there is something within the PSF of Hubble. If it is outside the PSF of Hubble, I mean, if you detect it, it's not a real companion. It's just another cluster member that happens to be very close. As we saw the other day, with the spectroscopic binaries, you can go out to periods of about 2-3 years, maybe. And perhaps in this case, because they are all emission lines, it's even worse. So you are ruling out a very close companion. A white companion, we haven't got the spatial resolution to say whether it is there or not.
So it's an emission line.
Yeah. They're all emission lines, these objects. They're all like...
Because they're post-main sequence already.
No, because they have extremely thick winds. These are these sort of things.
Oh,
you don't see the photosphere. These are hydrogen core-burning stars of 80 solar masses. And they look like that. They are all emission lines. It's just the wind. You just see the wind.
But even if you have an O2 main sequence star with a very small absorption line, you can hide that completely.
Yeah, probably you can hide it completely, yeah. It's tough.
Okay, let's thank Ignacio one more time. Coming up next is Lucio Meyer, who's I was debating, do I introduce this as he's going to talk about the formation of star formation, or as the most extreme environment in population 3 star formation and really the dawn of the first stars?
Okay, let's see. Because this is the one.
Okay, perfect. Take it away, Lucio.
Okay. So, yes, I'm going to talk about something very different. So we are switching gears and making a journey back in time by a lot. I'm trying to show you how the first stars formed, giving you the basic ideas and also some of the results that, especially numerical simulations, have produced in the last 2 decades. It's a very active field, and in addition to population 3 stars, I'm also trying to give you some ideas about another type of exotic object that should have formed, probably, in the very early phases of structure formation. These are supermassive stars. If you want, they are kind of the tip of the iceberg of the process of star formation. So the main difference between what I'm going to show you and what you have heard so far is that here you also need to care about cosmology. So star formation in the very early phases of our universe was tightly connected with how cosmic structure formation developed. So until now, in the lectures you have heard in the past days, you didn't need to know anything about dark matter. You didn't need to know anything about cosmology. But now we need to know about that. So that's why I'm going to ask you now, students, how many of you have taken already a cosmology class? Because there are quite a few. That's good. So sometimes I'm going to ask you quick questions just to check that we have the basics. And if not, I'll try to cover them. So baryons don't do much until recombination. But you know, anything that happens after recombination is what we care about for the formation of galaxies, but also, as you will see, for the formation of the first stars. So after recombination, baryons are in a very simple state. They are essentially metal-free, so you have just hydrogen, helium. And therefore, you expect that the thermodynamical properties of the gas will be very different from what we have heard so far for the present-day universe. In particular, as you will see, with this state of metal-free gas, the cooling is very inefficient. And even in the best conditions, you know, when the density and the temperatures, at the time when the process of baryonic collapse starts, are favorable for the collapse to happen, you can never reach temperatures below 200 Kelvin. As you will see, this is really dictated by the cooling properties of the primordial gas phase. As I said, cosmology matters, and it matters in many ways, not only because of the background physics, but also because gas collapses in dark matter halos, and that's where the first star formation will happen. Now, it's, I think, interesting to notice that the first structures, the first dark matter halos in which star formation happens, and I will try to explain you why they are these particular structures, are objects of about 10 to the 6, 10 to the solar masses, 10 to the 7 solar masses in dark matter. And they have a size that is roughly 10 to 100 parsecs. So it's maybe a coincidence, but there are objects of dark matter, halos of dark matter, that have roughly a mass and a size comparable to what you know is the mass and size of GMCs, of giant molecular clouds today. So just keep in mind this mass and size. You will see why that's relevant in a few slides. And these halos, so the nurseries of the first stars, appear around redshift 30. So as you probably know, structure formation in the current model of our universe, which is dominated by a form of matter which is cold, collisionless dark matter, is driven by gravitational instability of these cold dark matter components. So the mass of the baryons is relatively irrelevant for how structure develops, because it's about 1/6 of the mass of the dark matter. So the potential that matters is that of the dark matter. So instability driven by gravity will happen in the dark matter component, and the baryons will follow. Of course, so far we have no direct way to test any of the predictions of the theory in these very early phases. So it's really like theory's playground, if you want. And it's a lot based on many of the things that I'll show you are based essentially on numerical simulations. So just to check the basics, when, you know, to have a timeline in mind, when did recombination happen? Can someone tell me what is the redshift at which recombination happened? Yeah, that's right. And what is recombination? Just to make sure that everybody's on the same page. Right, and that means that what's the state of photons can escape, and therefore for the matter phase, what does that mean? What does that imply? Yeah, you can form atoms, exactly. So the hydrogen atoms form only after recombination. Before recombination, the coupling with the photons doesn't allow the binding energy to be below the first ionization potential of hydrogen. So structure formation, as I said, is driven by dark matter, by the gravitational instability in the dark matter component. And I'm sure many of you have seen pictures like this. This is one of the many cosmological simulations that different groups have run in the past 2-3 decades. This is quite recent. This is it's just a piece of the Euclid flagship simulation, which has been run in Zurich to essentially work as a data set to compare the actual data of Euclid and constrain cosmological models. And the main feature of these simulations that is pretty evident when you look at them is that halos of dark matter form hierarchically. So if you look at one halo that I identify a low redshift at the present time, and I try to trace back its formation down to very early times, what I see is that it's basically splitting up in smaller and smaller halos, and that's how it got to begin with, right? So it's small halos that come together, they merge, and they end up forming a larger halo. So that's the hierarchical picture of structure formation. That really depends on the fact that the dark matter that we are considering here is collisionless. So there is no interaction between dark matter particles except gravity. So it's completely driven by gravity. Now, we care about the baryons, as I said. And we are looking at the epoch after recombination when you have hydrogen atoms. And as you start forming the first dark matter halos, what this gas phase, this hydrogen phase does is eventually it will come close to the potential while of one of these dark matter halos. And if the potential while of this dark matter halo is strong enough, deep enough to bind the baryons will be captured gravitationally. And as they be captured gravitationally, they start falling inside the dark matter halo potential. And depending on the temperature that they acquire, you might cool at different rates. And we will actually look at what are the coolants that you have at this epoch. And if you're able to cool enough to form a very dense object at the center, if the gas also has some angular momentum, it will eventually stop and form a protogalactic disk, if you want to call it. So it will not continue to collapse down to the very center, but we'll find a centrifugal barrier. And in this protogalactic disk, you may begin to form stars. That's a general picture. And the other important point, which is true all the time, even for low redshift galaxy formation, is that when the gas falls inside the potential well of the dark matter halo, it will heat up. Before cooling, it will actually heat up because what happens is the acceleration driven by the potential of the dark matter halo increases the kinetic energy. And the kinetic energy then is thermalized, and therefore the temperature increases. And if you're not able to cool, so if you are in a situation where cooling is very inefficient, you will not actually continue to collapse. You will form a static atmosphere. So rather than a galaxy, you will just have a diffuse halo in virial equilibrium with the dark matter halo. So you need to cool in order to get down and form a protogalaxy. This is a generic feature of galaxy formation all the way from very high redshift to the first halos to the present time. What changes at very high redshift is the cooling properties of the gas. And here you see an example of the formation of a galaxy down to the present time. And you see all these gas flows that are coming together and arranging the protogalactic disk. This is basically this picture, but except that here you have a spherical cow model, and here you have a more complicated density field and velocity field due to the real pattern of structure formation. So the questions is, they want to answer is, when the first halos appear that are able to capture baryons and lead to the formation of a collapsed baryonic phase, which means also the formation of the first stars. So there is this concept that maybe some of you have already heard about in lectures, in cosmology lectures. If not, I'm trying to give you the basic ideas behind that. And that's a concept of the cosmological Jeans mass. So you have certainly heard, and actually you have heard it even in this week, about the thermal Jeans mass, and maybe even about the turbulent Jeans mass. This is similarly related to the balance between gravity and pressure. But here, gravity is not provided by the baryons. The gravity, again, is provided by the dark matter. So you can actually derive a Jeans mass for the baryons immersed in this dark matter density field, which is growing due to gravitational instability. And what you obtain is this expression here. So that's a cosmological Gibbs mass. It's basically the minimum mass that the baryons have to have in order to be bound to a dark matter halo. Right? So, and it turns out that the mass that you are talking about is of order 10 to the 4. So if you take typical values of omega matter and omega baryons, so the density parameters of baryons and dark matter relative to the total omega, the total density, the energy density of the universe, you get something that is of order, 10 to the 4 solar masses. So that's several times 10 to the 3 to 10 to the 4 solar masses. So at that level of mass, then you should start to see the baryons collapsing into the dark matter halos. Now, the way you get this mass is really through perturbation theory, so linear perturbation theory. So as you do for the normal Gibbs mass, the difference here that when you solve the perturbation equations, the source term on the right-hand side is not given by the density of the baryons, as it would be in the normal thermal Gibbs mass, but is given by the density of dark matter. Technically, it would be the sum of the two densities, but because the density of dark matter is dominating, it's basically the source term in the Poisson equation that matters. You can also get a similar estimate of the mass using a slightly better model, which is not linear perturbation theory, but it's kind of a nonlinear version of gravitational instability, and it's called the top hat collapse, where you're basically looking at little spheres that reach a certain characteristic density to turn over and decouple from the cosmological Hubble flow. And then you can look at what is the minimum mass for these little spheres of dark matter to capture the baryons and let them also to fall into them as they decouple from the Hubble flow. And you get a similar result. The mass is, again, about 5 something times 10 to the 3 solar masses for the typical cosmological parameters that you want to plug in. Now, let's say that we are at this mass scale of 10 to the 4 solar masses. Now, the other thing that we need to care about is the cooling properties of the gas. And by the way, you will see in a couple of slides that this cosmological Gibbs mass is actually a very rough estimate of the correct mass for the collapse, because there are other effects that come into play that make this mass higher. And you will see that in the end, the mass is really this 10 to the 6 solar masses that I mentioned at the beginning. Okay? But before that, the cooling properties of the gas. So you have hydrogen, and after recombination, what you have is essentially atomic hydrogen. It's not completely recombined. There's some small residual ionization, but it's extremely small. We're talking about 10 to the minus 5 or something. So most is really neutral. You don't have H2. So in the cosmological matter field, you have hydrogen, you have helium, of course. There's helium. Then there are trace elements of, trace quantities of deuterium, beryllium, and lithium, but they're really like less than 1%, so they're really not relevant. But you don't have molecules, so you will see that the molecules, the molecular hydrogen, you will actually form inside the dark halo potential. So when the gas falls inside the dark halo potential, the conditions will develop in such a way that you will be able to form molecular hydrogen. You don't have molecular hydrogen ready. So when the gas falls, it's just hydrogen and helium. Essentially, you have to care about hydrogen itself to understand what's going on. Now, if you were able to cool by Lyman alpha transitions, Lyman transitions, including Lyman alpha, with atomic hydrogen, this is the cooling function you will get. And then there's a correction for helium. So that's the black line that gives you the cooling in a gas essentially made of atomic hydrogen. And the cooling peaks between 10 to the 4 and 10 to the 5 Kelvin. If you were able to form molecules, in particular H2, then you would have this type of cooling function where the cooling peaks between 10 to the 3 and 10 to the 4, so about a decade smaller in temperature. Then there is another molecule that you can form early on, but it requires some specific conditions, so it doesn't form as efficiently as molecular hydrogen, that's HD. You have some deuterium, so you can in principle form HD that will play a series of reactions which I will not discuss, but just keep in mind HD also can happen in the early phases. But we will focus mostly on H2, because as you see, this will be actually the first significant coolant for the formation of the first stars. Now, if I say that here you have efficient cooling between 10 to the 4 and 10 to the 5 Kelvin, and here you have it between 10 to the 3 and 10 to the 4. Then the question is, can the gas that falls inside the dark matter halos have the right temperature so that I can have efficient cooling through this or efficient cooling through this? Right? So you need to have the right temperature in order for the cooling to be provided efficiently by either atomic or molecular hydrogen. And that's where cosmology again comes into play, because the temperature of the gas that falls into these dark matter halos depends on the mass of the dark matter halos in which it falls in. So this is an old set of plots from a very nice review of Barkhan and Loeb. This was one of the first reviews on first objects, maybe the first one actually, in 2001. And all the basic ideas were already clear in that nice review. So here what you see, let's focus on these first plots. What you see is two dashed lines. So this first dashed lines is roughly depicting the temperature, the threshold temperature at which cooling by molecular hydrogen would be relevant. Again, it's somewhere, as you see here, around 10 to the 4 Kelvin. That there is a redshift component, but we don't look into that. Let's say that it's around this temperature that you will have efficient cooling by molecular hydrogen at high redshift, between redshift 20 and 30. Then if you look at the atomic cooling threshold, so efficient cooling by atomic hydrogen, that's higher. But you want to first have a halo of mass large enough that it can actually be above this temperature, the one given by molecular hydrogen, so that molecular hydrogen, if it forms, can provide cooling and allow the collapse to happen. Now, the halo growth in these plots is computed using a semi-analytical approach. It's basically based on pressure injector. And the numerical simulations have shown many times that this works pretty well. So you have roughly the correct answer when you look at how halos grow from high redshift to low redshift. So here are three examples of growth curves for three sample halos, if you want. This is a halo that is kind of a typical fluctuation. This is a halo that is 2 times the typical fluctuation, so 2 times higher than the typical fluctuation. We say 2 sigma. And this is a halo that is 3 times the typical fluctuation. So 3 times is already pretty rare, right? It's 3 sigma fluctuation. So you see this 3 sigma I could also show the 4 sigma or whatever, but they become extremely rare and rarer. So usually people stop at 3 sigma to say that you look at something relevant. So at 3 sigma, you see that halos that would form, they would collapse and decouple from the Hubble flow somewhere around here, so redshift 35 or 40. By redshift 25, they start crossing this threshold, right? So the temperature in these halos, of the gas that falls in these halos, would become large enough to allow molecular hydrogen cooling to be efficient, if you are able to form molecular hydrogen, which is a separate question which we will try to address in a couple of slides. Why the temperature and the mass are related? Because again, what I told you before is the key thing, right? The gas falls into the dark matter halos. The kinetic energy that it acquires, that is accelerated by the potential, is thermalized and is converted into thermal energy. And so the halo gas has a temperature which is determined by being in equilibrium, in virial equilibrium with its dark matter potential. And you have very nice analytical scaling relations that you can work out for an isothermal halo. If you assume the halo has an isothermal profile, so it's an isothermal spheres, you can find this nice relation between the virial radius, the virial mass, the virial velocity, and the virial temperature. That's really what we care about. The virial temperature scales as roughly the virial mass of the halo to the 2/3. You can get it very easily by the fact that in equilibrium, you have the kBT vir is basically the proportional to the virial velocity of the halo square, and the virial velocity is proportional to the virial mass. This is coming from cosmology. This is coming just from basic thermodynamics, if you want, to assume equilibrium of the gas in the potential well of the halo. So that is because these halos of a given mass automatically have a certain temperature that allows them to be in the right regime for molecular cooling to be efficient. And as you can see here, we are talking about halos of a mass that is around 10 to the 5. And if you wait a bit longer, like about redshift 20 or 18, it gets down even to, it gets up almost to 10 to the 6. So 10 to the 5 to 10 to the 6. So that's a bit different from the previous cosmological Jeans mass. That was just to capture the baryons. But in order to cool efficiently, you need to be higher, so closer to 10 to the 5, 10 to the 6 solar masses. But then there is another further correction which may make your mass even higher, your critical mass for cooling even higher than that. And that's the fact that it's true that baryons recombine at redshift 1000, but the temperature of the baryons, actually this is a question that I've asked, maybe some knows already. Does the temperature of the baryons after recombination remain, no, I'm asking in a different way. Does the temperature of the baryons after recombination evolve separately from the temperature of the photons, or does it not? Who knows the answer? So after recombination, after redshift 1000, do the temperatures of photons and baryons evolve completely differently? Do they decouple completely or not? Anyone knows the question?
Binary answer.
I'm not 100% sure, but I think it's the energy of the matters decreased by the S volume. This also happened to the photon, but the photon wavelengths it's also become longer. So there's more.
Yes, but so I guess I can ask you the question a different way. Is there, after recombination, is there still some coupling between the temperature of the baryons and the temperature of the photons? There is still some mechanism that can couple them, or is it, or they are completely separate? I mean, not always this is covered in cosmology classes, so it might be that people have not heard about it. But so the answer is they are still coupled until redshift about 150. So meaning the interaction rates are basically zero, right? So the interaction rate is essentially zero or negligible because there was recombination. But you have this thing, this called inverse Compton. So there are still some free electrons that, because of inverse Compton, they still eat the matter through coupling with the ions, the residual ionization that is still around, which doesn't go to zero right away. So in the end, because of inverse Compton, if you look at the energy exchange between matter and radiation, this is such that the temperatures remain locked, the two temperatures remain locked until redshift 150. It's only at 150, so much later, that the two temperatures start to decouple completely. So it means that the baryons are a bit hotter than you would think if you were not considering this temperature decoupling. And what that translates into is that once they decouple at 150, then there is some residual velocity, thermal velocity of the baryons, which then decays like 1 over A, like, you know, the Q velocities in cosmology go as 1 over A, where A is the expansion factor. But it's such that it takes a long time before it becomes small enough compared to the velocity of dark matter particles, which is basically zero. So dark matter is basically zero thermal velocity because it's collisionless. But the baryons, even after 150, redshift 150, even up to redshift 20, have still some residual velocity, thermal velocity, relative to the dark matter. So that means that it's harder for the dark matter to capture them than in our simple picture, in which I was not considering an extra velocity. Okay? This is like an extra velocity which makes them harder to capture. So when people started realizing that, this is really recent. It's only in the last 10 years, 10, 15 years, that people realized that this effect might be important. So they call this the streaming motion of baryons. And so they looked at the effect. In numerical simulations, you can do some back of the envelope calculation and showing that this effect is important. There's also a thermal tail that is important. So it's not that all the particles have the same velocity, but you have a distribution which is essentially given by the fact that initially you had a kind of Maxwell-Boltzmann distribution of your constituents. And so when you look at them in numerical, you see that this is basically pumping up a bit more the critical mass for collapse. This is a model that actually is based on the simulations, and these are different results of numerical simulations. So they are not all consistent with each other, but let's say to be on the safe side, the mass now goes up to more than 10 to the 6. And so finally, we are back to what I said in the first slide, that the critical mass for halos to capture the baryons efficiently and form the first objects is somewhere between 10 to the 6 and 10 to the 7. This is including even the streaming motions of baryons. Okay, so now we finally got to this 10 to the 6, 10 to the 7 critical mass for the collapse of baryons and the formation of first objects. First objects means the first stars. Now, what happens as the gas falls into this 10 to the 6, 10 to the 7 solar mass halos, which people call mini halos, by the way. That's just jargon. Well, there are three channels by which you can form molecular hydrogen. And let me just tell you from the beginning that the formation of molecular hydrogen happens in the flow once it's already inside the dark matter halo, because that allows the flow to become dense enough for these reactions to be relevant. Okay, so you need the density to get high enough, and that happens once you are inside the potential well. And so as Mark already alluded yesterday, what happens in this primordial gas chemistry is that you need some ionization, and you can form molecular hydrogen through these two different channels, which all depend on the availability of free electrons and the availability of ions, like H plus in this case. In this case, it's really free electrons that starts the process. So you can form it in this way, or you can form it in this way, but both are pretty inefficient, so you get to molecular gas fractions that are never above 10 to the minus 3 of the total, 10 to the minus 4, 10 to the minus 3. This third process, which is triple interaction, is the one that gives you almost a fully molecular core inside this early halo, so it's the most efficient, but it only becomes relevant when the density is really, really high. So at the very deepest stage of the collapse. At the beginning, these are the two channels that you rely on. Notice one thing, that you need free electrons, you need ions, but I told you that we are looking at after recombination, when gas should be neutral. That's again another reason why you need the gas to fall in the potential well of the halos. So one is the density, that you need high density, and you get it and you fall in the potential. The other thing is that you fall in because you heat up, then you start to partially ionize the gas. So the halos are the key, right? Without the halos, nothing would happen. Okay, so that's basically the typical history, temperature, density history of gas that falls into this mini halo. So you imagine the gas is starting to fall in. As it falls in, it gets heated by the PDV work you do against gravity as you fall in the potential well. And then you get up to a temperature about 2000 Kelvin. And at this point, you start to have significant ionization, or enough ionization to start entering these two channels of reactions that I showed at the in the previous slide. Then here, at this point, you have formed a baryonic core which has about 10 to the minus 3 fraction in molecular hydrogen. Then you keep collapsing, because now you can cool a bit. Thanks to molecular hydrogen, you can now start to cool through the J2 to 0 autovibrational transition. And then the temperature can go down to about 200 Kelvin. That's what the molecular cooling can take you if you only consider H2. If you have HD, which you can have, but again, separate set of reactions, some more special conditions, so I'm not going to cover it, you could cool a bit more, roughly to about 120 Kelvin or something like that, but it's not a big difference. Once you are here, then, because you are in the very high density phase now, about 10 to the 3 atoms per cc, then the triple interaction channel starts to be important, and this is really what takes you to a fully molecular core. It's the triple interaction that you start doing here. Okay, now, what happens is, because you are collapsing even more, then you cannot cool even more than that, then you start to adiabatically heat, and that's why the temperature starts to raise again. And then eventually you get to a point where you start to collisionally dissociate H2, and then once you are at G, that collisional dissociation starts, essentially you are in a regime that is very similar to the onset of protostellar collapse in present-day star formation. So once you get it to G, you don't care about cosmology anymore. But up to G, everything happened because you are collapsing inside the dark matter halo of a certain mass, which gives you a certain initial virial temperature. Okay, so the first star simulations that people began to work on in the 2000s were based on these principles of structure formation plus early gas, primordial gas chemistry. And this is an example. This is the famous work of Tom Abel in 2000. This is the first simulation that was done at the time, where with dark matter and baryonic physics and the primordial gas chemistry, they could see the first example of formation of a protostellar core and let's call it a protostar at the center, this dot here. And they found that this object was extremely large, was a few hundred solar masses. So from that time on, for a few years, several other papers appeared by Tom and also by Volkerbrom and others, showing that, yes, you were forming systematically very massive protostellar objects inside these mini halos. And the justification was, of course, because the Jeans mass that you get is such that the gas cannot cool below a temperature of 200 Kelvin. That the Jeans mass is high by construction because of the temperature. So no surprise that the stars, the protostars, are extremely massive. But the early simulations had a problem, which was just due to the limitations that people had at the time in computing time and computing power. And that's the fact that they were only looking at small boxes, so just a small, they were carving out small regions of a cosmological volume in order to be able to get down to this, AU scale resolution, few AU scale resolution, and resolve the protostar. But if you do a small box in numerical cosmology, you have an issue that you are lacking to include the tidal field of the larger scale distribution of matter. And if you're lacking to include the tidal field, you are lacking to include a proper evolution of the angular momentum of matter. So you're running out of angular momentum relative to the correct answer. You have much less angular momentum than you should have. And so then it means that the gas flow, when it enters these halos, is essentially zero angular momentum. And then, of course, affects the way the collapse happens. Everything goes to the center, right? Then later on, people started to do the same simulations with larger boxes. And Naoki Yoshida in 2012 was one of the first to do that. This is one of the boxes of this set of simulations. So then here you have several objects that collapse at redshift 20 to 30. And you have a large-scale density field, so the tidal torques are efficient, they are correctly captured, and the angular momentum of the halos and the baryons is correctly captured. How do we know that it's correctly captured? Because you should have the same distribution that you have a low redshift in dark matter boxes, a low redshift, because it's the universal properties of halos. It just depends on gravity, there's nothing else. And the fact that the density field is not isotropic, okay? So when people started to do these simulations, they realized that you don't have this centralized collapse, but you have the formation of a protostellar disk, no surprise, like in present-day star formation. Now, the protostellar disks in these early phases of star formation are a bit different in a few aspects, and especially in one. So let me go back to what was discussed already by Mark yesterday, so the Tumri instability. So you saw this already yesterday. The Tumri criterion, that's a criterion that tells you if it becomes unstable in an axisymmetric disk. It's derived from linear perturbation theory, of course, so there's limitations, but that's something that we can correct in different ways. But let's say you have this Tumri criterion, you have to be less than 1 in order to have fragments forming in your disk, but that's not sufficient. It's a necessary condition, but it's not sufficient. The other condition that you need, which has been studied a lot, especially for protoplanetary disks, is the Gami criterion, the fact that the cooling time of the gas has to be smaller than the orbital time. Because if that's not the case, what happens is as the gas approaches this Q1, then you're starting to form the spiral shocks before you can actually fragment. And the spiral shocks eat the gas, and they tend to raise again Q. It's called the thermal regulator phenomenon. So the spiral shocks, they develop, and they re-eat the gas again. In order to combat this re-eating due to the spiral shocks, you need to have fast cooling. So this way you can keep going down to Q less than 1. Otherwise, it self-regulates and never gets to fragmentation. Now, there are two ways to do that. Well, of course, you have to have some, right properties for the gas chemistry and the gas composition so that you have efficient cooling. Or you can kind of circumvent the problem and saying, well, let's look at how how can Q evolve, right? So if you take the derivative of Q, right, basically this is the derivative of the three variables that appear in Q, so the sound speed, which is basically the temperature, the epicyclic frequency, and the surface density, okay? So if I have fast cooling, what I'm doing is I'm combating this term, right? This is the term which will tend to eat the gas, right? It's really related to the sound speed. If I have fast cooling, I will keep this term very low, right? So then Q can actually decrease, because this time tends to increase Q, right? This is negligible. The variation in epicyclic frequency, if the potential is not changing much, is basically zero. But then you have also this other term. This would be the change in surface density independent on the change on temperature. And it's a negative term, so we'll bring Q down if the surface density increases. So that's the other way you can actually bring your disk to fragmentation, is if you are dumping enough mass at a fast enough rate that the surface density increases fast enough that brings Q down faster than it can eat up through the spiral shocks. And this is something that has been understood in protostellar disk and protoplanetary disk already several years ago by different people in simulations and also analytical calculations. But what really matters here in the POP3 case is that the mass loading, the m dot of the gas onto the disk, is much higher than it is in the present-day star formation. In present-day star formation, the best case is like FU Orioni systems. You can infer that the mass flow through the disk is maybe 10 to the minus 4 solar masses, because that's what you measure on the star, so you could be saying they are proportional. But in these early phases of star formation, from the simulations, you measure m dots that are as high as 10 to the minus 2, 10 to the minus 1 solar masses per year. So 2-3 orders of magnitude higher than you expect in present-day star formation. So this is why all the simulations that can resolve protostellar disks in the POP3 star case find fragmentation. So this is one of the first ones that did that, the Clark et al. Paper, where they were showing the formation of a multiple stellar system. This is one example. They have many others in the same paper. Here they were forming three protostellar objects. And so from 2011 or so and later, then everybody started to realize that protostellar disks form and fragment vigorously. So you don't form a single protostar, you form multiple systems. Then just a little aside, and people also developed in the meantime also stellar evolution models for POP3 stars. This is a nice summary of the status of stellar evolution in POP3 stars in the Klesser and Glover review. Some of the earlier models were done by the Geneva group, Meder and Menet. And one key point that I'm going to use a couple of times later is the fact that if you look at the HR diagram for present-day stars and the one for POP3 stars, the POP3 stars, especially the very massive ones, they tend to be much hotter and more compact. And so that is important for the feedback part. Right? So just keep it in mind. The radius relation with the radius mass relation is different, and the typical radius is smaller, which gives them higher temperatures. Okay, so we have this, situation where now we have a protostellar disk that fragments. So the mass function, the way the mass distribution of protostars develops in this POP3 regime is, of course, heavily affected by this fragmentation. So you have always multiplicity. And then, of course, you will have to care about radiative feedback. And as I said in the previous slide, you expect this to be important because stars are hotter. So the UV flux, especially from the massive end of the stars, should be important. And that's actually what has been found in many calculations, that is extremely important to determine how the mass function evolves in these protostellar disks. In a way, this is not surprising because we know it's important also in present-day star formation. Magnetic fields, this is a relatively new area, so there's still not much, but there are some attempts to evolve the protostellar disk or even the cooling flow in the halo with an initial magnetic field. There is a recent paper that appeared last year by the group of Volker Brom that shows how fragmentation is affected by the inclusion of ideal MHD. They looked only at the field inside the protostellar disk, not the field in the cosmological cooling flow. And they find most of the times the fragmentation is reduced, so that multiplicity is going down, but they still have at least 2 or 3 protostars per system that form. There are other forms of instabilities driven by the magnetic field that have been recently studied in protostellar and protoplanetary disks that might be relevant also in POP3 stars, like the magnetic dynamo driven by gravitational instability, but they have not been discussed in the POP3 stars regime yet. Baryonic stream velocities, I discussed it already. Neutrino dark matter annihilation, that's pretty exotic, but there's been some work on it. So you can, in very dense cores of the very dense part of the mini halos, you could have some annihilation radiation produced by neutralino dark matter, which is a form of collisionless dark matter. That would also act as an heating source and affect the fragmentation of the disk. So in the Klesser and Glover review, there's a nice summary of the status of mass functions for POP3 stars with the different types of simulations done in the last few years, different approaches for radiative feedback. Some use ray tracing, some use simpler ways of looking at the transport of radiation. Others don't even have feedback. And so the bottom line is that there is one point in which everybody agrees that the mass distribution is relatively flat. So the mass function is flat, at least up to the point where they can follow these protostars, which is only a few orbits of the protostellar disk. And of course, if you have feedback, then you tend to form more massive stars. So you tend to suppress the low mass end of the protostar mass function. You can see that also the cumulative mass function. The two models with stronger feedback are the ones that produce relatively more massive stars compared to small mass stars. And again, this is not surprising. And then, another important point is the early phases are such that when the protostar forms, it's still accreting a lot. And so if you are in a situation where you're really accreting really a lot, like more than 10 to the minus 2 solar masses per year, then there are some nice star evolution models by the Japanese group of Hosokawa that have shown some time ago and have been confirmed by other groups that you will tend to generate a bloating of the star that becomes essentially like a very massive giant star and a supermassive red giant star, if you want, in terms of structure. So the mass-radius relation becomes completely different from the previous one. You have a very large object. This makes the object cooling down. The UV flux becomes then completely suppressed because the star then emits only the optical. So for feedback, once you enter in this very bloated phase, then it matters a lot that you do that because you suppress feedback, right? So if you get to this very bloated phase, which is when you have a high accretion rate, then feedback becomes irrelevant. So it's a different channel of evolution for these POP3 stars. But the interesting point is that if you keep accreting at these large rates, more than 10 to the minus 2 solar mass per year, for some long enough time, and the mass of the star keeps growing and growing and growing, then you become what people call a supermassive star. So we are going above 1,000 solar masses at this point. And then you enter another interesting physics route, which might lead you to the formation of a very big black hole, all the way directly from the collapse of the star. And that's something that was already hypothesized by Fowler and Hoyle in the 1960s. Chandrasekhar also studied this possible evolutionary track of very massive stars. So the main point here is then once you get to a mass of 10 to the 4, 10 to the 5 solar masses, the central density of the star becomes so high that general relativistic corrections become important in the core of the star. And that means that when you look at the critical adiabatic exponent for instability, which in Newtonian stars is 4/3, for polytropes is 4/3, in the case of general relativistic stars, it's actually a bit higher than that. As the star is very hot, it's accreting, it's being continuously heated, so essentially it's radiation pressure supported, it's very hot, then its intrinsic gamma will be close to 4/3. But even if it is slightly above 4/3, right, because it's in the GR regime, it might be already at the stage of instability. Okay, so this is something you can study in detail using pulsational theory for the general relativistic regime, and you find that it's very easy to bring the star below this gamma crit at which it will collapse all the way into a black hole. And again, because the GR correction make your effective gamma for collapse higher than in the Newtonian case. So it's easier to reach the collapse regime. So rotation can help to slow down this process and kind of suppress the growth of the instability at the center, but you need really a lot of rotation to do it. So if you grow above 10 to the 3, 10 to the 4 solar masses, the route to forming a black hole directly is very plausible. And this has been studied a lot recently by Lionel Amberley and also people in my group. And we have seen that you have this important channel of formation of black holes, of very massive black holes, that would happen in POP3. But even if you have a metallicity that is close to solar, it might still be relevant. And here you see stability lines. The plot is very complicated, but let me just say that if you have high angular momentum, which corresponds to F is the measure of the angular momentum, 1% of the Keplerian value, and here is 0 angular momentum. So if you have enough angular momentum, so rotation is important, but it's not super high, it's just 1% of the Keplerian value, then you can avoid the unstable regime until a mass of 10 to the 7 solar mass. So you keep the star growing up to 10 to the 7, and then you start collapsing. So if this is happening, then you would form a black hole of 10 to the 7 solar mass all the way, which of course a high redshift is an important consequence because we have these bright quasars at high redshift 6 and 7, even some close to 8 now, that we don't know how to explain. They are very massive. They are black holes of 10 to the 9, 10 to the 10 solar masses. And this would be a way, through the formation of supermassive stars, which you really have to think as the tip of the iceberg of the early generation of stars. And you can look at which halos are actually the best candidates, which type of halos, which masses, at what time are the best candidates for producing an M dot high enough to accrete for enough time to grow the star to these very large masses. And what happens is that you have two ways of doing it. So to get above this 0.01 solar mass per year, which is the interesting regime, you have to wait at least until atomic cooling halos appear. So that's redshift less than 20, 15. So the mini halos, where the normal POP3 star form, have an M dot that is too low. You will never get to very high supermassive stars. But if you wait long enough, because in cosmology, the gas inflow rate, the M dot, depends on the mass of the halo. You have a simple scaling relation. As you wait long enough, more massive halos appear. They form out of the hierarchical structure formation. And eventually you get to an M dot that is above this regime. This happens roughly around the formation of atomic cooling halos, so halos in which atomic hydrogen now is the main coolant, because the temperature, as the gas falls in, is high enough, 10 to the 4, 10 to the 5 Kelvin, that atomic hydrogen becomes your main cooling channel. So that's, again, redshift 15 or 20, so quite later than the very first generation of stars. But if you wait even longer enough, even longer, then you get to redshift 10, and at redshift 10 you have halos. The first halos appear 3 sigma peaks of 10 to the 12 solar mass, already as large as the halo of the Milky Way, but we are at redshift 10. And in this case, the M dots that you can get because of the scaling relation can be huge. They can be more than 100 solar masses. And once you get to 100 solar masses, essentially, you can grow the star to even 10 to the 6, 10 to the 7 solar masses before the collapse sets in. So you will form really a very, very massive black hole just by collapsing directly these supermassive stars. So this has been studied a lot recently by different groups. This is just one example of a work from one of my students where we got this range of masses for the black hole from more than 10 to the 7 to even in some extreme situations for very hot inflows, we could get even up to 10 to the 8 solar masses. So the transition to the subsequent generation of stars in metallicity can happen very quickly. I will not discuss it a lot. We are almost at the end. So I can just say that as soon as the metallicity is getting to about 10 to the minus 5 solar, then you start producing efficient, you start switching already to a situation where dust matters, and then also molecular hydrogen will start to form in the way that Mark has described already yesterday. So it doesn't take a lot of metallicity. Already at this stage, again, simulations have shown that you switch to this 2.5 regime, so it's not really population 2, but is already quite different from population 3. And also the mass function becomes very different. You are dominated by stars that are less than 1 solar mass. So it looks already almost identical to the present day star formation. And we are at redshift. In some halos, it might happen already at redshift 20. In other halos, a bit later. It depends on how how early the star formation has been initiated in a given halo. And let me conclude by saying that if you ask about observational evidences of POP3 stars or supermassive stars in the early universe, in the early times, we are starting to have some. Of course, it's very difficult, but JWST is clearly going to change the field in that sense. So we're starting to have some observational hints that these things exist. So these are some recent results that I'm just popping up that have advocated the discovery of a cluster, potentially a cluster of POP3 stars. The metallicity has been measured through spectroscopy and is very low, so it's consistent with essentially, the upper limit is 10 to the minus 5. So of course, it could be 10 to the minus 5 or 10 to the minus 6, which would be already too high, but it could also be 0. So it's a good candidate, and it has been observed thanks to lensing. So in order to see a cluster of POP3 stars at redshift 10 or so, higher, you need lensing. Even with JWST, you will not be able to do it without the magnification effect of lensing. But that's why this object was observed, thanks to magnification. And so maybe there will be other candidates that will come up soon, so stay tuned because this is becoming very interesting. There are other ways that you can actually infer the existence of POP3 stars, even indirectly. For example, you can do it by doing galactic archaeology, and so trying to reconstruct the metallicity evolution of the most metal-poor stars in the galaxy and connect them to the enrichment done by the first generation of supernovae. You can do it also in galactic satellites where you have a better chance to find good candidates because there are more metal-poor stars in galactic satellites than in the Milky Way. There are also some interesting effects in cosmology that might be used to detect the presence of POP3 stars indirectly. This is something that we should be able to measure with SKA. This effect is basically such that if you had POP3 stars, if they are massive enough to produce a high enough UV flux at early times, and you get UV flux and you get also Lyman alpha photons. The Lyman alpha photons change the spin temperature of the hydrogen in intergalactic hydrogen, so they have an effect on the intensity of the 21 centimeter signal. So for SKA, this could be something that might be observed. And then for supermassive stars are a different beast because since they become extremely large and they are structurally similar to a big red giant, then the temperature is low. So they are actually in the JWST bands. So they would emit in UV, say, optical to UV, but mostly optical. And so they might be observed directly because they're very massive, they're very bright. So if they are not enshrouded in a very dense cloud which blocks the radiation, they might be detected directly. But they might also be detected by gravitational waves because as they collapse, the collapse will not be perfectly symmetric, especially if there is rotation. And there are many predictions that they should emit a high enough burst of gravitational waves to be detectable by the laser interferometry space antenna in the next decade or so. And I'm going to stop here.
Hey, anyone have any questions? I owe you a chocolate, too.
I'm not sure I understand correctly, but you said that to make the direct collapse supermassive stars, we need to wait for the high mass halos to form and with high accretion rate. So does that mean that we should not form any of stars before that forming that supermassive stars because there's some feedback that can hurt some accretions?
Yes, so right, so it's again, you have to think about this always as a statistical problem, right? So you have some halos that form first. These are the 3 sigma peaks that I was showing at the beginning. These are the ones in which the first stars will begin first. In these halos, of course, you will start to have star formation early on. You will probably photoionize the gas very quickly. You will, remove the gas from the halo. So they're not good environments for having a very high M dot. But then as you wait long enough, the same halos are growing, growing, and growing, right? And even if you had formed the first stars at redshift 30, as the halo grows, it reaccretes the gas at later time with an M dot that is much larger, it could still be a good place to form the supermassive stars.
Okay. So given some numbers for that requirement for that the condition of the formation of that stars,
Yeah.
it is plausible to find those high mass halos
To find what?
To find that conditions in reality.
Yeah, I mean, we know, so the halos, for example, atomic cooling halos, these atomic cooling halos at redshift 15, 20 become the most, redshift 15, they're really the most common type of halos. So, they are the halos where protogalaxies form. So basically what you could phrase the problem a different way and say, in the halos where the first protogalaxies form, so they are large enough that a real protogalaxy can form, not just a few individual POP3 stars. In some of these halos, you can imagine the galaxies forming, but then the central flow becomes so intense in M dot that can form the supermassive star at the center. But outside, you have a protogalactic disk, you have normal star forming. So it's, if you want, you can think of it as a scaled up version of the accretion disk of a black hole.
First, thank you for the lecture. I will have two questions.
Yes.
First is also about these supermassive stars with which you showed, like, but you had in calculation up to 10 to the 9. Is it like, how do you reach this limit? Is it also rotation allowed you?
Yes. Yeah. So so in this complicated problem, the paper of Lionel, which I recommend to read because it's very nice. It's quite tough to go through, but it's very nice because it tries to really, include all the physical ingredients to understand how the instability depends on the different parameters. And the key point really is the fact that in order to get to a star that is above 10 to the 6, 10 to the 7 solar masses, you really have to have rotation. But you don't need a lot of rotation because, again, let's look at the POP3 star case. So if you have, again, metal-free star, then these are stability lines. So it means that if you are to the left, you are stable. If you are to the right, you are unstable. Okay? And then you can say, where should I be, or which stability line should I be if I want a star of 10 to the 8 solar masses, for example, right? So then I go and say, okay, 10 to the 8 solar masses, okay? Then which instability line I encounter here, if I have 1% of rotation relative to Keplerian, so it's not a lot, it's 1%, then I encounter this stability line, which tells me, let's see, here 1%, let's say here, okay, more or less, okay, here. 1% is about here. Then at 1%, I encounter this stability line, and this is about 10 to the 8. If I ask, okay, I have less angular momentum, I have just 0.5% of Keplerian, which is the stability line, is this one, I go here, the mass is 10 to the 6. So as you reduce the angular momentum, then you go down in the mass that you need in order to become unstable. And eventually, if you have 0 angular momentum, become unstable at 10 to the 5. Right? So in other words, to form a very big black hole from the collapse, you really need to have at least 1% of the angular momentum in relative to Keplerian. Yeah.
Okay. And another question is about this star formation episode in galaxies. We were told in previous lectures that they formed in H2 clouds.
Mm-hmm.
So in this case, I mean, it was, as I understood, it was clouds because we need to have H1 surrounding area around them, so no far UV radiation will destruct H2 moleculars. So in this case, when we don't really have any sources of far UV radiation, is it really a clouds or it is more like disturbed around?
Yes. So that's a good question. Yeah. So to be honest, we still don't know exactly what is the configuration of the ISM when this type of object would form. The simulations that my group and other groups have done are still quite idealized. So for example, in this case, I just popped it up before without actually having time to explain it. So this is one example of a simulation where we have conditions that in terms of m dot would be favorable for the formation of a supermassive star. So this is a proto-galaxy inside a halo at redshift 10 that has merged with another halo. So during a merger, you get, by construction, a very high m dot. This is true also low resh, because mergers drive a strong inflow of gas to the center of the merger remnant, because you have these strong tidal shocks that remove angular momentum. Okay? So in this case, the region where the m dot is large enough, it's near like a 0.1 parsec scale region where the m dot is more than 100 solar masses per year. So you would grow the star very fast, and it's rotating. So you would have enough angular momentum. It's more than 1% the Keplerian. So it would delay the collapse up to, you get maybe to 10 to the 7, 10 to the 8 solar masses. You have a sort of disk-like system. So it's not really a cloud, right? So it's a flattened disk-like system, essentially.
Thank you.
Yeah.
We probably have time for one more. Yep.
So just now, one of the plots that you show has, it's plotting temperature against the density, where it looks a bit like this. And afterwards, it shoots up to really high temperature.
Right.
Yeah, that's okay, it's not too high. I'm just wondering, the fact that the temperature is rising with density, does it have any effect on the further collapse during the process? Because you mentioned it has to be cool enough.
Yeah, so
for the process to continue to collapse into a object and form stars.
Yeah. So let me clarify, just in case it was not clear. So here at stage C, you have reached the lowest temperature that you can get primordial gas conditions. Okay, so you cannot cool more than that, because that's how the J2 to 0 the rotovibrational transition of molecular hydrogen will take you. Okay, 200 Kelvin. So that's, the coolest that you can get to. But the gas, so this is taken from a numerical simulation, right? So what happens is the gas continues to flow in from the cosmological field, right? Continues to flow in the halo. And because it continues to flow, then the density continues to increase, but you cannot cool anymore.
Right.
Therefore, you have to expand, right? Because as you increase your density, your PDV work also becomes higher, but now you have no way to cool because you're already at the coolest temperature. So that's why you start heating up again, right? So it's adiabatic heating, basically, okay? And then, you have to wait until you get to this stage. The temperature now gets close to 2000 Kelvin, so that's the dissociation temperature of H2. Once you get to this stage, then you can collisionally dissociate H2, right? And then it's like the present-day protostellar collapse regime, where you will start cool again because of dissociating H2, right? So after this, you will start cool again, and you form your protostar through the dissociation of H2. So that's to the right of stage G.
Right. Sure. Thank you.
Okay, so I believe we now have a coffee break, and following that, we are going to break into some discussion groups. So Rainer, do you want to talk about what we're going to be doing for the discussions?
Yes, just a second. Thank you, Ben. Thank you, Lucio. Thank you, Ignacio. We will have, so as you know, at 12:30 we will have the Institute seminar here. So now we have a coffee break. Until 11:30, let's extend it a bit. It should be 12 to 12:30, so 11:30. We then come back here. We'll then split into 3 groups. We take you to different rooms to prepare tomorrow's, well, we call it final discussion. I wouldn't say so much should be a discussion. It should be more like a conversation. And the idea is to split into 3 groups with tutors. So basically, again, we go with the scales, small, intermediate, and large. And just talk among yourselves about what you find interesting, what you found controversial. And kind of the idea for tomorrow is to identify the most important directions where our or your research should go. Just be back here, let's say so we have a full hour for these 3 discussions, which is more than sufficient, so I would say let's meet at 11:40 here to split up. Okay, now